So in today's lesson, we're going to investigate the resistance of a wire. So you'll be able to state what's the independent and dependent variable in this investigation. You should be able to state the control variables when investigating to ensure we get a fair test. You'll be able to measure current and potential difference in the circuit. You'll be able to use Ohm's law to calculate the resistance of the wire using the current and the potential difference. You should be able to calculate the resistance of the wire and plot a graph of length against resistance. And for some of you, you might be able to explain the idea of electron flow and how that affects resistance. So firstly, in a minute or two, we will do a starter on series and parallel circuits. I'm then going to introduce you to Ohm's law and how we calculate resistance. Then I want you to practice applying these to questions. Once you're confident at doing Ohm's law, I'm going to show you a practical introducing you to how we can investigate how the resistance of a wire depends on length. I'm going to take you through the practical, which I've videoed, so you can see the results and the graph plotted. So first of all, have a go at this starter. What you need to do is just write down what the meter readings would say. So B is an ammeter, C is an ammeter, D is a voltmeter, E is a voltmeter, F and G are both voltmeters. Have a go at that. I'll go through the answers in a minute. So we've got a parallel circuit here. We've got 6 amps flowing here. So B would read 6 amps as well. Notice the current splits here. If 2 amps flows that way, then 4 must flow that way to add up to 6. Here we've got a series circuit and we've got 2 identical bulbs. We've got 6 volts, so that will read 3 volts and 3 volts as the voltage is shared in series. Finally, if you remember from last time, in a parallel circuit, the voltage is identical to the power supply, so both those would read 8, so F would be 8 and G would be 8. If you got all those right, well done. So now I'm going to introduce Ohm's law to you so we can look at how we can calculate resistance of components. Resistance slows down current. Voltage pushes the current through and resistance slows it down. So if you've got a high resistance, it means it's harder for current to flow, and if you've got a low resistance, it's easier for current to flow and the charges move around faster. So how would we work out which component has the bigger resistance? Suppose I gave you a bulb and a buzzer and said, find out which has got the bigger resistance. So we need to use Ohm's law to calculate resistance. And Ohm discovered the potential difference is equal to current times resistance. Current potential difference is measured in volts, current's measured in amps, and then Ohm decided to use the Greek symbol ohm to represent the unit of resistance. So that is omega, a very odd looking symbol. Now we can put this into a triangle to help us rearrange, because potential difference must go at the top because the 2 bottom things multiply together and we've got current times resistance. So if we want to work out what current is, we would cover up current and its potential difference divided by resistance, that's underneath, like a fraction, 4/2. So current is potential difference divided by resistance, and resistance is equal to potential difference divided by current. And that is the equation we need to work out the resistance of different components. So resistance is potential difference divided by current. So what you could do is you could take the bulb or the buzzer under test, you'd attach it to a power supply, maybe 6 volts, and you'd measure the voltage across your bulb, your component, by connecting the voltmeter in parallel. And of course you'd put the ammeter in series to measure the current flowing through the component, and just measure both of those and do potential difference divided by current, and then you could tell me which has the higher resistance, the buzzer or the bulb. So what I want to do now is have a go at some practice questions using Ohm's law so you get familiar with it before we go on to investigating the resistance of a wire. I'll do the first one with you, then I'll let you have a go, pause the video and have a go at the rest. So when a light bulb is connected to a 12-volt battery, a current of 3 amps flows through it. Calculate the resistance of the bulb. So we just use Ohm's law. Resistance is potential difference divided by current. And so I've written the equation out first, so I can't now get it wrong. 12 volts goes there for voltage, potential difference. We've got 3 amps for the current, and that equals 4 ohms, the resistance of the bulb. So go on to Show My Homework now, and you'll see this worksheet on Show My Homework. As well as that, at the bottom of the worksheet is a writing frame if you're finding it a bit tricky to calculate the values. If you're using the writing frame, it shows you the equations that you need to use. And finally, the end of that are the answers. So go through, do that, check your answers, and then come back to this video and carry on with the resistance of a wire. I hope you did well on the Ohm's law questions. What we're going to do now you're confident at using Ohm's law, is to look at a practical to investigate the resistance of a wire. So have a think about what the resistance of the wire actually depends on. Well, the first thing it depends on is the length. Now, to help you understand why it depends on length, here I've got a picture here with the charges or electrons that flow through the wire. Now, when they flow through the wire, they actually collide with the atoms in the wire, which slow them down as they pass through. And so you can imagine that if we double the length of the wire, then these electrons have got to flow past double the number of atoms. And so you'll have double the collisions, which means that will slow the current down, and therefore the resistance will go up. And actually, you should find that if you double the length, the resistance doubles. Now, another thing it depends on is the thickness of the wire. So if you double the thickness of the wire, you can see we've got double the amount of electrons in this part here. We've got double the area for them to flow through. So actually we can get double the number of charges passed, which means the resistance halves. So the thicker the wire, the lower the resistance. Now in our experiment, I want to get over the idea that when we talk about the wire having resistance, then students start to think all my connecting wires that I use have a high resistance. So I just want to show you this. This is the circuit we'll be using. We'll have a power supply. We'll have the connecting wires, which are really thick. And then we're going to have a very, very thin wire that with a wire under test that's stuck to a meter ruler that we can change the length of. Now I just want to show you with this magnified photo, you can see clearly that the wire, the connecting wires, are incredibly thick compared with the wire that we're going to test. So these connecting wires really have no resistance whatsoever, very, very low, so won't affect the experiment at all. The only thing that will affect the resistance will be this very thin wire here. And finally, another thing which affects the resistance of the wire is what it's made out of. So different metals have different numbers of electrons in them. So of course, if you have a metal with many more electrons in, then it will conduct electricity better and have a lower resistance. And finally, the last thing that the resistance of a wire depends on is its temperature. So of course, when a bulb heats up to really high temperature to produce white light, its resistance goes way up. So what we've got to do in this experiment is to make sure that we keep the temperature of the wire to a very low value so that it doesn't increase the resistance. We're going to investigate how length of a wire changes or affects resistance. What I want you to do is have a think about what you think the independent variable is, what do you think the dependent variable is, and what do you think the control variables are to make it a fair test. Pause the video, have a go, and I'll go through it in a minute. So the independent variable is the one that we're changing, and we're going to change the length. Of course, the resistance will depend on the length, so that's the dependent variable, and that's the one that we're measuring and calculating. And finally, because we only want to find out how length would change resistance, we've got to keep other variables the same. So we've got to keep the thickness the same by using the same wire. We've got to keep the type of metal the same by using the same wire. And we've got to keep the temperature low, so that doesn't affect the resistance of the wire. So we can use a very low current to stop the wire from heating up. So how are we going to do this experiment? Well, you've got a meter ruler with a length of wire on it. You've got to measure the current flowing through the wire and the voltage across the wire in order to work out the resistance. And we're going to plot a graph of resistance against length. To change the length of the wire, we've just got a crocodile clip connected to this end and a crocodile clip connected here, and we can move the crocodile clip up and down the wire to change its length. We're going to start with a length of 20 centimetres. Anything smaller will start to heat the wire up. So we're going to keep the current low, start at 20 centimetres, then calculate the resistance and plot the point. Then we're going to repeat it for 30, 40, 50, 60, 70, 80, 90 and 100 centimetres. I'm going to now show you the video that I've done of this practical so you can see how the results work. So I've got a series circuit where current flows through the ammeter. If I connect the crocodile clip at 20 centimetres, it will flow through that part of the wire and then back to the power supply. So that's our series loop. We've also got the voltmeter connected across the power supply in parallel to measure the voltage across the length of wire. I'm also going to reduce the voltage, so I take the current down so it doesn't produce heating. So with a length of 20 centimetres, we get a current of 1.06 amps, a voltage of 0.99 volts, and if we divide voltage by current, we get a resistance of 0.93 ohms. And I'm going to plot that on our graph. So now I'm going to increase the wire to 30 centimetres and measure new current and voltage and work out the resistance voltage divided by current. Follow the rest of this video to show you how we get the final results and also the graph. If we plot the best fit line, we can see we've got a straight line going to the origin. This means that resistance of the wire is directly proportional to length, which means if we double the length, we double the resistance of the wire. I now want you to write your own conclusion for this experiment. What happens to resistance of the wire as the length increases? What shape was your graph? Does it go through the origin? And you could sketch the shape with the labels resistance and length. And finally, what happens to resistance if you double the length? You can find that out by looking at the graph or the table of results. So finally, have a look to the learning objectives just to make sure that you are familiar and you are confident that you can do most, if not all of those. Next week, we're going to be going on to magnetism and then on to electromagnetism. Have a good week. Bye for now.